So the next talk is given by Stefano D'Angelo. Yeah. He has given a short presentation this morning for his poster, and now the compiler is running, so we will have formulas by you without starting our own compiler in our brain. So, Stefano, we are looking forward to your talk.
Okay, thanks a lot. So I'm here to present this other paper on anti-aliasing method and a general anti-aliasing method for SINE hard sync. So a brief tutorial on BLEP, BLAMP, and related methods. So essentially, let's say that we want to generate a sawtooth waveform that has less aliasing than using a trivial method. The first thing that we can notice is that such waveform, the harmonic content and then also the aliasing content that we will have in the digital domain for this waveform is located in the discontinuities. And indeed, if we remove them, we just get a straight line, which is a signal with no harmonic content. So we know, one technique to reduce the aliasing from such a waveform in the digital domain consists in subtracting some residuals, so-called residual functions at each discontinuity. This technique is known as BLEP, which means band-limited step, and indeed you do that and you get an anti-aliased version of your sawtooth signal. So, for those who don't know, hard sync is a feature of many old synthesizers, but maybe also new ones, but certainly the old ones, where you have two oscillators. One is the master and another is the slave. And when the phase of the master wraps, then also the phase of the slave is forced to wrap. So essentially, in this case, for example, we have a master oscillator that has a lower frequency than two slave oscillators. And we see that what happens actually on the output waveforms in case of the sawtooth and a square wave. Now, the same consideration that we did before is possible to apply to this case. So essentially, the same technique can be applied also for hard sync. The only caveat is that you need to scale the residual for sawtooth waves when the sync happens. Now, let's move to triangular wave. In this case, we don't have discontinuities, but we have a similar situation because the discontinuities are in the derivative of the triangular waveform. So essentially, the same considerations apply, and just we need to use another kind of residual, which is called band-limited ramp, which is actually obtained by integrating the band-limited step. In this case, I just had to scale it a little bit for it to be better visible, but that's the same idea and the same principle. So what happens if we do hard sync on a triangle? Well, we have two kinds of discontinuities this time. We have normal discontinuities, on the triangular waveform itself, and the discontinuities on the derivative of the signal. So essentially, we can combine the two techniques pretty easily, and we can still obtain our anti-aliased version of this signal pretty easily. Now the problem starts with the sinusoid, because in the case of a sinusoid, as everybody I hope knows, it has an infinite number of derivatives that are not zero. So essentially, when you sync, you create an infinite order discontinuity in all of the derivatives. One might be tempted to just limit himself to the first few, but this doesn't work well in the digital domain because when the frequency of the slave oscillator is relatively close to Nyquist, it's the higher order the higher order derivatives that have more that determine more aliasing content. So yeah, in theory we should apply BLEP, BLAMP, and an infinite number of other similar techniques. But yes, so if the paper exists, it means that we have found a solution to the problem. First, we redefine the problem in a proper way, in a useful way for us, which is we define the waveform that we want to anti-alias as a waveform that before time 0 it's the unsynced sinusoid, and after for t bigger than 0 it's the synced sinusoid, as you can see. So the trick here is to decompose the signal into the unsynced sinusoid plus a sum of shifted one-sided sinusoids with an appropriate amplitude and phase. And please notice that all of these sinusoids have the same frequency. Then what we want to do is actually convolve this signal before with a low-pass kernel before sampling it back. So essentially, the convolution operation can be shown to be equal to the convolution operation of this signal with the low-pass kernel can be shown to be equal to the unsynced sinusoid plus the convolution of this kernel with each of the one-sided components. And this is true as long as the kernel that we are using is, when convolved with the unsynced sinusoid, gives us back the unsynced sinusoid itself, which means that it will have unitary gain at that frequency and zero phase. So this is the same formula that I've just shown on the previous slide. What we want to do now to make this approach practical is to express the same thing in terms of residuals once again. So essentially, we will just, well, these three formulas do just that. R is the residual, G is the target function, and F is the original function. So it's probably intuitive, but it can be shown that if the low-pass filter that we choose is finite length, then also the residuals have the same support as the impulse response of the low-pass kernel that we've chosen. So the question is whether we can compute the residual or the target function by a finite number of operations. Unlikely there's not much to say about this. You just carry on the computations and you get the results. So we've done it for polynomial and bit splice type kernels and for trigonometric kernels, in the sense of kernels that are sums of cosines. The formulas that are shown here are not exactly the same on the paper, but they are here just to show a couple of properties. So you will find different formulations there. Essentially, for polynomial and B-spline kernels, we get that you need to compute just a few polynomials, one sinusoid and one cosine. While for the this is per residual. For the trigonometric kernels, instead, we have to compute multiple sinusoids and cosinusoids, and we have a few constants that depend on the frequency of the signal. But of course, since these sinusoids and cosines are multiple, their frequencies at integer multiples, they can also be potentially obtained by Chebyshev polynomials. So we have tried to see what happens, comparing our approach to no anti-aliasing and the previously best known method. Both in the case, the master frequency is higher and lower than the slave frequency. We have used, for the previous method, which is pretty flexible itself, we have used the same length for kernel, the same kernel length. And the previous method uses the Kaiser window, while for our method, we chose to use the triangular windows because it's one of the simplest that you can use. As you can see, you can tell me if there is an improvement. And also in the other case, we get similar results. So the improvement is pretty dramatic. So conclusions. We have better aliasing suppression than the previous method using the same kernel length. We also have lower computational cost than the previous method because we just need polynomials and sinusoids and cosines, while the previous method needed the evaluation of the exponential integral function, which is pretty heavy to compute. We have found explicit formulations for kernels that are polynomial, B-spline, or trigonometric. This methodology is very general, so it could be applied to any FIR kernel as long as you can cope with the math, which is not obvious. And theoretically, the same approach could be used could be applied to other waveforms that have this kind of properties where we have infinite or very high number of discontinuities in the derivatives, such as, for example, for polygonal oscillators. Finally, the code is on my personal website. You can go and grab it, and that's it.
Thank you very much.
Don't leave.
Any question?
No question.
Do you have a further remark? You mentioned the implementation depends on your FIR window, which you need there. So what's the additional complexity to perform these convolutions?
What do you mean exactly by that?
You mentioned you have a sinusoid input, and your filtering operation is just working on these jumps in your signal, and there are convolutions happening, or is it just repeating the waveform and shifting that?
I mean, the convolution is used to derive the final formulas. So essentially, those formulas here will just be the actual implementation of the anti-aliased output.
Okay.
So you don't need to do any convolution. It's a tool to obtain these formulas. Okay. And of course, if you choose your kernel in different ways, you would obtain different formulas.
Yes, and what's the general capital P or capital N there?
I should remember that. Yeah, P is the order of the polynomial. N is the N is the number of cosines that you use to generate the window.
Okay.
So I don't remember if Hanning uses 2, 4, or 5. Yeah, it's that number.
Okay. Yes.
So if I may just advance that question. So the larger the N number or the larger the P number, the better performance you can get. I mean, we've seen that the performance is great already. I mean, the reduction of aliasing is very significant, but with those, I mean, the level of reduction depends on those parameters that you choose.
Yeah, those are parameters that are related to the kernel. I mean, they are defined by the kernel that you choose. So if you choose a better kernel, you get better suppression. You can go as far as you want with this.
Okay, great.
I have a question on the application of these methods. Do you plan on combining with oversampling for respecting when you are, for instance, at 44 kilohertz? You can have maybe a little bit. You have a little bit of low pass on the waveform. So, do you use it with oversampling?
You can use it with oversampling, of course. It's not sampling frequency dependent, so you can do pretty much what you want.
Okay, if there's no more question, then thank you very much again, Stefano.